So I've got some notes for you about sound. And the topics in this set of notes are we're going to talk a little bit about what sound really is, the speed of sound and how it changes with temperature, the idea of sound intensity and sound intensity level, and then talk about the Doppler effect. So sound is basically longitudinal waves in air and fluids. It can be both transverse and longitudinal in solids. And it's the result of some sort of a vibration or wave disturbing matter. So it's disturbing the molecules in the air. And if you think about a stringed instrument, it kind of makes it easy to understand. When you pull on the string swings back and forth. And when it goes in one direction, it compresses the air. And when it moves back the other way, it expands the air. And you get a compression, and then you get what's called a rarefaction. And that is a whole pulse or wave in a longitudinal wave. And hearing is how our brain interprets that change of pressure that comes with the wave, the compressed air versus the expanded air. And one of the other things that's a perception-related idea with sound is pitch. And so a high pitch is going to go along with a short wavelength or smaller musical instruments, higher notes, and the low pitch is going to be a longer wavelength, lower notes, bigger musical instruments. Speed of sound is 331, 343. You've seen different numbers for speed of sound, but the reason you've seen that is two different things. One, it depends on temperature, and the other, it depends on the material it's going through. So it should make sense that sound and other waves will slow down when they go through denser material. So if you're underwater in a pool, sound is moving slower. The speed of sound is also related to the temperature of the material, and this includes the temperature of the air. So the speed of sound changes depending on the temperature. You can see the equation right there. It really is a proportional change with temperature based on a Kelvin scale. So you do have to change temperatures to Kelvin. So here's a quick example. At a fireworks display, you hear an explosion 4/10 of a second after seeing the burst, because sound is slower than light. And so if the temperature is 25 degrees C, how far away are the fireworks? So we've got all of our givens. We've got our time, which is 4/10 of a second. We have our temperature in degrees C, so we want to change that to Kelvin. And then we have our 0 degree speed for sound, 331 meters per second. So we need to find how the temperature has changed the speed. That's our first thing. And then we need to use one of the distance equation. Distance is velocity times time, to find out how far away the fireworks were. So we talked about we talked about wave intensity, and here's a relationship for sound intensity. Intensity of a wave is power per unit area, and when we're talking about sound waves, we're talking about pressure changes in air or some other material, and so we can relate it to pressure changes, where the pressure variation is the max pressure minus the minimum pressure divided by 2, so it's an average. And the rho in this equation is the density of the material the wave is traveling through. And it should make sense that the greater the pressure or the greater the amplitude, the more air is compressed. It's a little different. Sound intensity level. Sound intensity level takes the sound intensity and puts it in a relationship that's lined up or calibrated with human hearing. And so you start with the baseline intensity for human hearing, which is 10 to the minus 12 watts per meter squared, and call that 0. And from that, you get this calibration type equation, which is logarithmic. So it's got powers of 10 in it to determine how the intensity relates to decibels of hearing. You can see on the chart on the side, 0 is just at the line where we start hearing, and then 40 decibels is just quiet, and 80 decibels is shouting, And 110 decibels is pretty much standing next to a rock band with loud speakers. Here's an example, paying attention to the idea that you've got to look for sound intensity versus sound intensity level to find out what you're using and when you're using it. So what's the sound intensity level that's 7 decibels lower than an intensity of 4 times 10 to the minus 9 watts per meter squared? And so our intensity is 4 times 10 to the minus 9 watts per meter squared. And remember that our threshold intensity is 1 times 10 to the minus 12 watts per meter squared. So we can find the decibel intensity level for the sound at that intensity, and we find that to be 36 decibels. Take the 7 decibels off. So next we have the Doppler effect. And the Doppler effect is basically a change in frequency due to the motion of a wave source. So when a car with a loud radio or an ambulance comes by, the sound changes as it passes by you. It starts at a low pitch, and then as it drives away from you in the other direction, it's a high pitch. And where that comes from is the motion is causing the waves to be compressed in front of the moving object and stretched out behind the moving object. And you can kind of see that in the picture. If that car is moving towards the girl standing at Y, the wavelength is shorter, and so that's going to increase the frequency that she's going to hear, and it's going to cause her to perceive a higher pitch. It's a little tricky with the equations. There are 2 equations. One is for the observer standing still and the source moving, and the other is for the source standing still and the observer moving. So you've got to be very, very careful with your situation. You have to identify what's moving and what's stationary, and then carefully consider the direction of motion, whether you're going to use a plus or a minus in your equation. So here's an example. We have a jet flying by at 1,200 kilometers per hour. It's emitting a sound that has a frequency of 400 hertz. And if the speed of sound is 342 meters per second, what frequency does the audience member hear? First thing you have to do is decide what's moving and what's standing still. So the jet's flying by, and our person in the audience is standing still. So we know we're going to use the equation shown here. We're going to collect up all of our givens, and the first one is the velocity of the plane. Change that to meters per second. Watch out for those units. We have our frequency, and we're given the speed of sound at that day, at that temperature, so we don't have to do any temperature conversions. So then we plug it into our equation. The frequency that the observer hears is equal to the source frequency, and then we have, in those parentheses, we have the velocity of the wave, which is the speed of sound, and then we have underneath in the denominator, we have the velocity of the wave plus the velocity of the source, which is our plane. And when you do all the math, you end up with 202.6 hertz. Alrighty, bye-bye.